This is the ROS Developers Podcast, episode 54.
The ROS Developers Podcast, the ROS Developers. The ROS Developers Podcast, the ROS Developers.
Hello, ROS developers, and welcome to the ROS Developers Podcast, the podcast that gives you insights from the experts about how to program your robots with ROS. This is Ricardo from The Construct, and today I would like to dedicate this podcast to all those people that are porting packages from ROS1 to ROS2. You know, ROS2 is still in its early stages, not so early, but I mean, it's not fully functional yet, and in order to become fully functional, it requires still a lot of work to be done by those people that are translating or making new packages for ROS2. So for all of you who are working on that thing, then thank you very much, and this episode is dedicated to you. And today, it is my pleasure to introduce you Steve Macenski. Steve is open source robotics engineer lead at Samsung Research America, but before that, he was leading the robotics team at a company called Simbe Robotics, where he was building fully autonomous store-auditing robot solutions. At present, Steve is the primary maintainer and developer of several ROS2 packages, like the Navigation 2 package, the robot localization, and today's subject of the podcast, that is a package called Slam Toolbox, well, a set of packages. He is also a member of the ROS2 Technical Steering Committee, and he is going to talk today about his Slam Toolbox package, among other things. So welcome to the podcast, Steve.
Hi, thanks. It's great to be here.
Okay, yes, I'm super happy that we finally made it, that we finally achieved to find the time where we can be together on the same interview and talk about your amazing Slam Toolbox package. Because
yes,
it was a little bit...
always hard, but...
Yeah, it was difficult to agree on the time, and so we have been after this for several months already.
Yeah, I think we had the conversation for a few weeks, and we finally scheduled at 7 a.m. on a nice and windy morning in San Francisco.
Yeah. Okay, so now it's 7 a.m. there. Oh,
yes.
Okay.
Yeah. It's a little early, but I end up going to work anyway fairly early. I think it's nice to get in early, leave early.
Oh, okay. So really appreciate it for this effort. Thank you very much, Steve. And And then, so you are working in developing ROS2 packages. So which packages are you working on?
Yeah, so I'm kind of working across the ecosystem, both things that I've developed in the past I'm porting to ROS2, some new things that I'm working on that are only going to be available in ROS2, and then just a lot of things in the ecosystem that just need updates to work in ROS2, so things like image pipeline, I'm a maintainer on that. Navigation 2, which is the second generation of the navigation stack, specifically for ROS2. There's a lot of really interesting changes that we've made there. And then robot localization is another big one. So I'm working with Tom Moore over at Localization Robotics to port that over to ROS2 and all the other good stuff that goes along with that while we're waiting for their Fuse package to come online. And some of the new things that I'm working on are I think, kind of interesting. The last maybe 2 months or so, I've been kind of going on a machine learning kick. So I'm thinking about packages around LiDAR-based machine learning tools. I think that's a really unique opportunity inside the mobile robotics community, where maybe doing straight-up neural net or deep learning with images, maybe not realistic for many people's platforms. A lot of people are running on these ruggedized, 4th gen i5 CPUs that just don't have the power needed to run, some of these modern things. But LiDARs are 1D or 2D, 2D or 3D.
2D or 3D.
So there's a lot less information coming in to process. So you have a lot more ability to do some interesting things with machine learning on these LiDAR data coming in that you might not be able to do on cameras otherwise. So that toolkit is kind of surrounding things about labeling, using RViz and these other tools that we have available to us. How do we train this? How do we build environments for training these things to do things like detection or glass and mirror compensation, and then being able to deploy that then on actual assets in the field. So that's something that's not open source yet, but it's something that I'm kind of been fleshing out the last couple of months.
Oh, that's amazing. I find this very interesting, this idea about applying machine learning to the LiDAR. And it is true that usually it is applied to the images, and of course they require so powerful computers. But for LiDAR, it's the amount of, or even for point clouds maybe, it's the same principle. So that would be a LiDAR in 3D, yeah?
Yeah, definitely. Images are so heavy, and running convolutional neural networks is also fairly heavy. And the expense of these computers are going down and down and down. Right? You can get an NVIDIA Jetson TK2 board for something like $600, and we are seeing some robotics companies moving over to that platform. And they're going to be able to run convolutional neural networks at 20, 30 hertz to do the things of interest to them. But I think for a lot of people, especially in the industrial environment, LiDARs aren't going away anytime soon. So let's try to use them as much as we can, especially with the computational resources that they have available.
Uh-huh. And then you mentioned that you still haven't published anything yet about those machine learning to LiDAR.
Yeah, so I have a repository that I'm working on under, but I don't tend to open things up until they're at a certain level of maturity, because otherwise you'd see all of my half-finished projects. So I like to make sure that it's at least at some level of functionality before it's open to the community. But it will be open source, so it'll be available. Whether it takes a couple months or maybe a year or two. Some of these projects really change in the time frame.
Yeah, I understand. Okay. Just wanted to be sure, just in case that we can provide something to the listeners, because the listeners are developers, they want to try and so on. But it's okay. We are going to provide some other packages, interesting packages that you already have developed, and they are already open source. Like, for example, these famous, like in the title of this podcast, is the Slam Toolbox. So what is it, this is Slam Toolbox?
Yeah, so Slam Toolbox, if people have followed some other projects, I'm horrible at naming things, so if there's a name out there for this, someone feel free to let me know. But essentially, it's a LiDAR-based SLAM for very large and dynamic spaces. So things like warehouse, retail. I have emails from people from libraries that are interested in using it. So these kind of large repetitive spaces, and it's just a 2D SLAM. Package that follows, RDP 105, so it's a drop-in replacement for Carto, Cartographer, Hector, G-mapping, these kinds of things. And originally kind of started as trying to replace Carto, Cartographer, G-mapping, because I just wasn't getting the performance and reliability that I wanted. Cartographer I found crashed a lot. I was really kind of unimpressed by the amount of data it required. It wasn't very consistent in these repetitive environments like retail and warehouses that you see that a lot of real robotics applications are put in. They have a really strong team. If you've ever actually read their paper is exactly how I would make a SLAM solution if I were to start from scratch with infinite time and infinite resources. But in practice, it just doesn't seem to work as well as I would like to work for me. And I've heard kind of a similar thing from other robotics companies in these spaces. So it just didn't quite meet my specs. Then there's Carto Slam, which is not very widely developed. I think the last substantial pull request was from 2016, which is now almost 4 years ago. But it is the SDK that's under the hood of Slam Carto. The Open Carto is used actually by a number of well-known robotics companies as the basis of their kind of internal Slam system. So there's some good heritage there, but it's just not very feature-rich. So Slam Toolbox builds on top of this Open Carto SDK, as well as a lot of modifications to the Open Carto SDK itself. If you look at the code, you're going to see that most things look familiar to you, but there's a lot of new capabilities in the postgraph and the optimizer and the scan matcher, taking advantage of multi-threading, things like this. Originally, when I was doing all these case studies with Cartographer and Carto and Hector and all these other SLAM packages, I found that SRI will sell you a professional version of Carto. I said,
yes,
I would love. Sorry, go ahead.
I was buying that one. Well, not me, but the company I was working at that time. It's called Simbe Robotics, and we were buying this license of Carto.
Yeah, so I really wanted to buy it from them, and so I said, "Oh, awesome! This thing is here. I'd love to try it out, see if it makes sense for us." SRI, let me give you money. Is essentially what I was trying to do. On their website they talk about that they have some localization, some offline tools. It's a little bit faster than the open source version of it, and a bunch of other kind of small things on top of it. So go to the website, hit the contact button, link's dead. I go to their email contact form, the message field doesn't work. Go on LinkedIn, try to find somebody who works on it, couldn't find him. Phone number, none to be found. And so eventually, after several weeks of me trying to get in contact with SRI, I finally just gave up and said, let's just do it ourselves. And actually, before this podcast, I tried to find this link myself to send you a screenshot. And yeah, the website's just totally down now. Like it doesn't even exist. It's like this. You couldn't even buy this right now even if you wanted to. A lot of what Slam Toolbox is the professional Carto tools that they would sell you on top of all of the stuff that Cartographer does, on top of what all the stuff that all the other Slam packages do, kind of put into one giant toolbox. And that's why I call it Slam Toolbox.
Okay.
Ton of tools that are put together on top of this very mature technology that's been further modernized.
Okay, makes perfect sense. Then, if I have correctly understood, then you in your Slam Toolbox, in order to create those dynamic and large maps, you actually need to have the original, let's say the original algorithm. It could be Carto algorithm, or could be Gmapping or Cartographer. So you still need them running.
No. So,
okay.
So when we're running, so right now, kind of the heart of this is OpenCarto, where really the only thing we're using from that is their original scan matcher code, because it's excellent. I think even the laser scan matcher package within ROS also uses the Carto scan matcher that's been pulled out of OpenCarto. It works extremely well. It's extremely fast, and there's a lot of other tools around it that OpenCarto also gives you. That's if you looked at Carto Slam, that's the SDK that they're calling.
Then I didn't understand what you mentioned, that is your Slam Toolbox is something on top of those Cartographer or Carto or Gmapping. So what do you mean that is something on top of it?
Oh, sorry. So it's its own Slam solution. So you don't need to have Carto, Gmapping, Cartographer running installed. You don't need any of those things. I was just trying to explain kind of the heritage behind the scan matcher library that we use inside Slam Toolbox. Just pulled out from OpenCarto.
Okay. Then you are just using from OpenCarto the scan matching, but then the rest of the Slam algorithm is something developed by yourself and your team, I mean.
Yeah. No? There's also, even the scan matcher has actually been modernized quite a bit. If you're familiar with the TBV library, it's I think it's an IBM library, maybe it's Intel, that basically blocks up large chunks of computation and spins up threads appropriately to process it. So we're actually speeding up the scan matcher quite a bit using multi-threading.
Okay, and then this toolbox, does it work for ROS1 or ROS2 or both of them? What is the status?
Yeah, so right now we're supporting kinetic and melodic, but it is my intention to support ROS2 dashing before ROSCon at the end of October.
Oh, okay, nice. Okay, so maybe, are you going to attend the ROSCon?
Yeah. So I'm actually speaking about this package at ROSCon.
Okay, you're one of the speakers. Okay, so we'll have the chance to meet there then. And then we can do a live demo, actually. So, I mean, you can show me.
Yeah, definitely. You can also look at my README file in the project. I'm a huge fan of just very colorful READMEs that have lots of moving pictures and images and things like that. I think it really gets the point across to people that, hey, this thing works. It's not just some grad student's project. It's a thing used in production by real robotics companies in real places, and it works.
Yeah, I can certify that you like this, because in your Slam Toolbox page, you put a lot of GIFs, an animated GIF around there, and then at the end you conclude with another animated GIF, so people can enjoy this.
Yeah. My other big project, the spatiotemporal voxel layer, which I talked about last year, ROSCon, also has just lots of GIFs. I'm a huge fan of visual demonstration, because you can't you can't necessarily fake visual demonstration nearly as easy as you can just lie in words.
Okay, yes, and also it's very useful for the people who goes there and then what to expect, so they can see what to expect. Okay, very good. So you mentioned in the documentation about your Slam Toolbox then that you are creating. You are doing mapping in two different modes, synchronous and asynchronous mode. Well, what are those two modes, and why could they be interesting for the listeners?
Yeah. This also might be another case where I'm horrible at naming things.
Okay.
What I view, So I'll start with asynchronous. So asynchronous is what you're going to see from basically every other online SLAM system. So what's happening is that measurements are brought in from a laser scan, usually the laser scan message from ROS, and they're checked if they're valid. Where valid meaning that the robot has moved a certain distance or a certain orientation or a certain amount of time has expired, and so that this laser scan should be potentially processed by the SLAM algorithm. And then it's checking that it's also a best effort system. So if for some reason the last iteration of the SLAM algorithm took longer to process than maybe the prior ones, or the map is getting large, and so it's taking more and more time to optimize the graph, then you're going to be dropping a lot of these laser scans, because the buffer in ROS is going to expire these laser scans over time, and you're only going to get so much of your map completed. So if you're moving at 1 meter per second in a 1 million square foot facility, there's a large chance that you're going to, as the map grows and grows and grows, that there's going to be a lot of these dead zones where you did get valid laser scans, but since the last SLAM system is best effort, you're not going to be processing those scans because they're dropped by the ROS system. Where synchronous is that we're going to be processing all valid measurements. So rather than doing the SLAM algorithm in the callback of the laser, we are going to be putting those into this buffer. And regardless of the processing time, we're going to be going through the entire buffer of valid measurements and making sure that we process those things. Where that's potentially bad is that the map then could lag behind the robot as it's growing larger and larger and larger. But if you're joysticking the robot, or if you're trying to do offline mapping, or you're collecting a bag file to do offline, then this is the best option. And then if you're also working in facilities that are less than about 150,000 square feet in size, synchronous mode is going to work 100% real time. So you don't need to worry about it. It's only when you start looking at these very, very large spaces where if you need to be mapping right now because you're using that map to navigate or do collision avoidance, then maybe the asynchronous mode is good for current mapping, but then you save that data to process offline using synchronous mode.
Okay. In your Slam Toolbox, at the beginning when we started talking about, then you mentioned that you are doing this for very, very large maps, and especially also for lifelong mapping. So why it is important to have this lifelong mapping ability or a skill into an autonomous robot?
Sure, yeah. I mean, I'll take a step back there and kind of talk about, what is lifelong mapping. So, lifelong mapping is this idea of taking a map that you've built and then you keep building on it or refining it over time. So how cartographer will do that is it will have these submaps that you serialize and then you deserialize when you want to create a new trajectory. And then you're going to be adding more and more of these submaps. This is going to grow unbounded, obviously, because if you keep adding more and more information, you aren't removing information, the processing time will keep increasing. So we have a similar capability as that. So what we're doing is letting you build this map, but then serializing the pose graph that contains all the nodes constraints of all the individual scans, as well as that raw scan data, rather than serializing some sort of submap. What that gives you then is a totally lossless serialization of your map, which then you can read in later to do some sort of offline manipulation or graph merging or anything else you'd like to do. Localization mode that isn't based on just image files, but based on the data itself. And we have the same problem as cartographer, right? Is that as you keep growing the map, there's more and more nodes, more and more scans, more and more memory being used, more CPU to process the graph. So something I'm working on right now, which will be also available before ROSCON in October, is a lifelong mapping mode as well, on top of the synchronous and asynchronous mode. And what this has is a bunch of carefully engineered algorithms in order to decide which nodes to remove over time and which nodes to promote over time, so that you are able to have this kind of living, breathing map that you're going to be continuously updating over time. So rather than just adding, when you add an individual node, it's going to be looking at its neighbors and say, how much more information do these neighbors provide me? And if the answer is not very much, or that the information is now stale, we're going to be demoting those nodes over time until that they actually eventually expire. So we're removing those nodes and removing that data, so that we have this kind of living organism of a map that's just continuously being updated, but is still bounded to some realistic graph size.
Okay, that's amazing, and it's very, very interesting, because it sounds to me like you can also afterwards, with a proper tool that I don't know if it exists, but you can kind of do a manual photo editing of the map, but just by attacking the nodes, the different nodes and their information that is associated to each node. Is that possible? So I can decide myself afterwards, and decide, because maybe there is an error. All the algorithms, none of them is perfect, and especially when we are talking about in very, very large spaces, so there are usually problems. So maybe there is one part of a big map that has been misaligned at some point in time with the other big part, so they look like not real. The whole thing together doesn't look like the real one, but it's just because in an area was produced an error for whatever the reason. So you can, by using your toolbook and your way of building this map, you can go and manually edit that node or set of small nodes that is making this misalignment, creating this misalignment, and then realign manually then, and then all the rest will be possible. Does it make sense what I'm telling you?
Yeah, 100% possible. Yeah, because when you I give you a bunch of tools, including the serialization, deserialization tools, and when you serialize each of these post graphs, you're getting all of the nodes and constraints as well as the actual raw data itself of each of the scans, which means that offline you can go and be processing this data and just say, hey, there's 6 or 8 nodes that are connected over here that are correct, but something weird happened. You can just select them, remove them, re-raster the map, and then now have your new updated map image. But I think something that's even slightly, in my opinion, more powerful actually about this library is that you don't even need those map images at all anymore, right? If you have these serialized data files, that is all you need. You don't need to have this image rastering of the map. That's useful for things like AMCL, using that image to do its particle filtering and its model updates. But in our case, you don't need it, which I think is amazing, right? That this just isn't.
Then the localization doesn't make a scan matching against the a given image of a map, but is making the matching against the different measurements that have been done along the way. Is that what you mean?
Yeah, exactly. So where AMCL is going to be taking your map file and trying to match between your laser scan and your image, this is going to be taking your serialized graph file and it's going to be matching against the nodes, constraints, and data that exists already in the post graph losslessly. So you're not having any sort of alias features from AMCL. You're not having to have this image file potentially that is this monolithic thing where you map. You have this image file. It's now for the most part not changeable. It's just now an image file where I guess you could go into GIMP or something and wash out some certain areas or try to have some keep out zones or something. But you can never reload the SLAM problem and continue to refine it or to manipulate it in other ways. One of the demonstrative applications I give you in the toolbox is this graph or this map merging tool, where this is I kind of show in this tool how in 300 lines of code you can deserialize any number of these maps that you would like. In RViz, you can drag them to align with each other using interactive markers, and then you can hit build composite map, and it's going to build a single map file that consists of those end maps combined, as well as give you that composite image that you would if you might want to use that for AMCL or something. But that's just a demonstration. You could easily do what you were suggesting, where you have this large map file, and say you have this area where there's a large glass window, and so you've got a lot of these erroneous measurements that you don't want. Yeah. You could build an application very easily to just drag through 5 or 10, drag a box around 5 or 10 of these nodes, and just say, hey, these nodes I want to raster with only a 5-meter range instead of the 40-meter range, and then rebuild your map on the fly, and now your image looks much nicer that you might use for collision avoidance or navigation or AMCL if you don't want to use my localization mode or whatever. But having this post graph and this raw data, it just really unbounds a number of really interesting opportunities, including map merging, multi-robot cloud coordination of mapping large spaces, and a lot of different interesting things like this.
Yeah, because now that you mentioned about the multi-robot, so by using your approach, then that means that you could have several robots that are contributing to the creation of a single map for all of them, because all of them, they are publishing those different nodes from their own perspective, but they are contributing to an actual single structure of a map.
Yeah, definitely. Yeah, absolutely.
So have you tried to apply with multi-robots?
Yeah. So I have some demos that I've done in-house, some proof of concept to show that it works. But right now I don't have it available in the toolbox for various reasons. But it is something that I hope to support in the future. But at the moment, I just don't work for an organization which has the need for it.
Okay. And one question about this localization system that you are proposing. Well, actually, you have implemented it in the toolbox. It's so have you had the chance to measure the performance of this localization system? Because when you are working in large environments, there is a problem of mislocalization very easily, because many places, they look like the same in terms of scan matching. So if you have a large space, then this mislocalization can happen more often. Did you have the chance to measure this or see if your algorithm works better than the typical AMCL?
Yeah, so AMCL, right? The A in AMCL is the adaptive, meaning that if for some reason the robot thinks it's in the wrong spot, it might jump to one place or another. But that doesn't happen when you map spaces. So rather than trying to list numbers, let's have a more like higher level discussion about what is the difference between mapping and localization. So when you're mapping a space, have you ever seen a robot just jump across like the warehouse? No. If you're running a graph based SLAM system, there is no particle filter for that to occur in. So when the localization mode that I'm presenting here is essentially making localization as close to graph SLAM as humanly possible, so that you don't have any of these weird artifacts that happen from running things like AMCL. So the actual localization quality of the localization mode, you should expect it to be on par with the accuracy of the map itself. So if you map the space and it mapped at this, you have this deviation, that's the deviation more or less on the same order of magnitude that you should expect when running in localization mode. Because we're not trying to localize off this rastered image like AMCL is, where you have these these rays coming out, and you're doing some sort of modeling of that probabilistically to say how likely each particle is to where it is. You're just literally matching based on which nodes constraints in the local neighborhood, and then updating your position appropriately. And kind of to go into a little bit more detail of how this works is that we're keeping this rolling window of scans that are being added to the post graph over time. So if you have a new scan in localization mode, it's going to be added to the post graph. The data is going to be added to the data file, it's going to be added to the optimizer, and you're going to be running the optimizer as you need to. Then after this rolling window of scans expires, that particular scan, it's going to be actually removed from the map, removed from the graph, removed from the optimizer, so that the map is actually going to revert back to the underlying file that you would save from your mapping session. So no data is being changed long term in localization mode, but in the local time horizon, you're going to be refining your estimation of that map. So what does that do for you? So when you have a forklift or a box or a person in the way, rather than in AMCL where you're raycasting through that box and saying, oh, hey, my ray is at 10 meters, it really should be at 12 meters because that's where the wall is. You view that measurement as potentially bad, or you're weighting particles poorly because of it. Instead, we're actually adding that box or a forklift or person into the map itself. So you're using the current state of the environment to help localize against the current environment versus viewing the current set of changes in the environment as deviations from some sort of map. So
okay.
Kind of the phrase I use is like, we're trying to make localization as close to SLAM as possible.
Okay. Yeah. Okay. So amazing, and a lot of information here to understand here and to process still yet. I think that the best way that we can do is to make the listeners to go straight to the Slam Toolbox and then download the code there and start doing their tests and then see what they think and how any application that exists at present that any real robot that is out there using your toolbox.
Yeah, there's several. So Simbe Robotics, my last company where I worked on Tally, the robot there, they've been using Slam Toolbox for Slam for over a year now. There's a handful of other companies which, I'm not going to out anybody by telling them, people who have had private conversations, but I can say that there's upwards of 200 robots I know of that are using it, probably more, but this is also a relatively new package. My last kind of big project, the Space of Temporal Voxel layer, that didn't really start to gain much traction until after my ROSCON talk. So I'm kind of expecting that after ROSCON this year, I'll be hearing more and more people using them.
I hope so. So please, ROS developers listeners, then please go ahead and check this amazing package. It also contains several tools based on RBIS, for example, that will help you allow this merging of the maps and visualization of other interesting information about the current status of your map. So one final thing. So you mentioned that you are going to have this for dashing by the ROSCON, yeah?
Mm.
Yeah, finally. Okay, so we'll wait for that, and then we'll add a link once you present this. Actually, we are going to add a link to your presentation, your actual presentation, so to the link into this podcast beneath the show notes. And once you have presented this and the ROSCON, then we'll also include this link, so the people who is listening this podcast some month later, they can just go straight. If you are listening to this some months later after the ROSCON, you can go to the show notes and see the current version in ROS2.
Yeah.
Okay.
I think one of my recommendations for
sure.
First people using it is to definitely go directly to the localization mode. You don't need to have some sort of serialized graph already, and just drive around and kind of get a physical understanding for what the localization mode is doing. You're going to be building this kind of local map that's being updated over time, and then it disappears when you leave a certain area. It's kind of like LiDAR odometry, and I think it's a really good kind of physical intuition for building of how the localization mode works once you have a map file that you're using with it. And it's available on Docker, it's available as a snap, it's available as a Debian through the ROS build farm. So, any way you want to install it, there's lots of ways to install it.
Okay, perfect. And do you provide any ROSback with information that they can use to also to test about building a map?
Yeah, so a separate project of mine that I've been working on is actually building a large open source data set of different spaces where, interesting places for both SLAM research as well as just kind of, robotics companies who might be interested in a space like, warehouses, factories, retail stores, banks, office buildings, things like this. But right now that's not open. I don't have enough critical mass of data yet to kind of launch that. But eventually it would be. But if somebody's looking for some data, feel free to email me. I can probably shoot you over some data.
Okay, so listeners, so you can email Steve. I will put the contact details here on the show notes of this podcast, and that is all. So thank you very much, Steve.
Yeah, thanks for having me.
Thank you, and see you at the ROSCon. And for all the listeners, let me remind you that if you want to become a roboticist or maybe an AI researcher applying to robotics, so you need to learn ROS. And because ROS is becoming the standard in robotics, actually it's already the standard. So how can you learn ROS fast? How can you do it? Very, very simple. Have a look at the Robot Ignite Academy. We have created the 30-70 teaching method based on 30% of the learning time, learning the theory, and the 70% of the time practicing with simulated robots. We provide a complete path for beginners, starting by teaching you about Linux and Python for robotics, and then we continue with the basics of ROS and how to build your ROS robot based step by step. Have a look at robotignite.academy. And that is all for today. Thank you very much for listening. See you next week with a new lesson from the experts. And until then, keep pushing your ROS learning.